In the last lecture, we were examining the oscillatory flow in a pipe driven by an oscillatory pressure gradient, okay, dP dx, which is k cos omega t. Okay. And we had written down the equations, the momentum conservation equation in the x direction, which contained the unsteady term on the left, the pressure gradient, and the viscous term on the right. And recall that we had scaled the radius by the pipe radius. Time scale was basically the frequency times time, and we had two options to scale the velocity, either based upon the viscous scale or based upon the inertial scale, okay, and we had chosen the viscous scale for our problem. And in this equation, so finally we got an equation of the form the Reynolds number, where Re omega was equal to rho omega r square by mu. Okay, Re omega was equal to rho omega r square by mu. This is equal to minus cos t plus the viscous term. We had made two substitutions. We had written cos t as the real part of e power I t and the velocity as the real part of a complex velocity field, which was the solution of the unsteady equation with forcing given by this e power I t. Okay. And to get the actual velocity field, we just have to multiply this solution by e power I t and take the real part of it. Okay. So, we had got an analytical solution for this in terms of Bessel functions, if you recall in the class before the previous one, okay, that satisfied both the boundary conditions. Okay. And for this I had also plotted the velocity field for you. Okay. So, the solution was this one. Okay. I have to take the real part of Vx tilde e power I t, where Vx tilde is this, and then I get the solution for the velocity field. I can of course plot it numerically. Okay. I can of course plot it numerically, okay, and I gave you the solutions numerically at different times along the phase of the pressure field, okay, at different times along the phase of the pressure field as shown here. Okay. And we were trying to get some physical insight into why the velocity field has this particular form. Okay, we were trying to get some physical insight into why the velocity field has this particular form. First, we looked at the low Reynolds number limit, okay, and I said that if Re is small, you can expand. Re is a small parameter in this problem. Okay, if Re were equal to 0, then you just have this equation 0 is equal to minus 1 plus 1 by r star d by dr of r dv okay. If Re is small, you would expect that this would be a small departure from the Re omega is equal to 0 solution. Okay. So, we had expanded the velocity field in a series in Re omega. We had expanded the velocity field in a series in Re omega, okay, and then substituted that into the governing equation, okay, and collected coefficients of equal orders in Re omega. So, first we collected what happens if you set Re omega equal to 0. Okay. In that case, you get this first equation. If you set Re omega equal to 0, you get this first equation. Subtract this from the original equation and then calculate all the coefficients of Re omega power 1, and you get the second equation, and so on. Similarly, you get the first, second, third boundary conditions, and so on. Okay. So, this leading order equation, okay, so this leading order equation, when you set Re omega equal to 0, that is the one that has the inhomogeneous term, and that can be solved to obtain this. Okay. this equation subject to the boundary condition. Okay. Substitute that into the equation for RE omega power 1, okay, and solve it. So, that Vx naught is the inhomogeneous term on the left side in the equation for RE omega power 1, and we get the solution for Vx 1 and then for Vx 2 and so on. Okay. And I had given you some physical insight into why this Vx 0 turns out to be of this particular form. Okay. Based upon the solution for Vx 0, okay, the solution for Vx star, okay, if you include only the term, okay, only the viscous terms in the equation, it turns out to be identical to the solution you would have, okay, turns out to be identical to the solution you would have for a steady pressure gradient. Okay. And that I had explained to you on the basis of a physical interpretation of this Reynolds number RE omega, okay, a physical interpretation of this Reynolds number RE omega. So, I will go over that once again. Okay. RE omega is equal to rho omega r square by mu, which is equal to rho r square by mu into 2 pi divided by the time period of the oscillation, of the pressure oscillation, okay, which is equal to r square by nu, kinematic viscosity. Mu by rho is the kinematic viscosity, into 2 pi by the time period of the oscillation. R square by the kinematic viscosity is the time required for diffusion across the pipe of radius r. Okay. The r square by nu is a time scale, which is basically the time required for momentum to diffuse across a distance r. Okay. So, this is the diffusion time divided by the time period into 2 pi. So, when the diffusion time is small compared to the time period, that means that momentum is diffusing over the cross section of the pipe much faster than the time period of oscillation. Instantaneously, the velocity field is assuming the value that you would get for a steady flow, because the time scale for the pressure variation is much longer than the time for momentum diffusion. So, therefore, this Reynolds number can also be thought of as the ratio of the time scale for diffusion divided by the time period of oscillation. So, that is a physical interpretation. Okay. RE omega is the time scale for diffusion divided by the time period of oscillation. When this is small, the time scale for diffusion is much smaller than the time period of oscillation. Therefore, the momentum diffuses over an interval of time much smaller than the time taken for the pressure to change. Therefore, the velocity field is identical to what you would have for a steady pressure gradient. Okay, with the amplitude of the pressure gradient equal to the instantaneous value at that instant of time. Okay. So, that is a physical interpretation for low Reynolds number. Let us look at the high Reynolds number limit. Okay. Recall that we had scaled the velocity using the scale for low Reynolds number. Okay. So, therefore, it is necessary for us to rescale our velocity so that the inertial and the pressure gradient are comparable in the equation in the leading order. When we had scaled our velocity based upon the viscous scale, the implicit assumption was that the pressure gradient and the viscous term in the equation are comparable. Okay, and that is why we had scaled the velocity by the viscous scale, and the inertial term is smaller or comparable. Okay, but there is a balance between the pressure gradient and the viscous term. At high Reynolds number limit, you would expect there to be a balance between the pressure and the inertial term, and therefore, we have to scale the pressure gradient the velocity differently. We go back to our original equation, partial Vx by partial t is equal to minus k cos t star plus mu by r square in this equation. I have not yet scaled the velocity. Okay. I can get a dimensionless equation by dividing throughout by k. Okay. I get a dimensionless equation by dividing throughout by k. Okay. So, if I divide throughout by k, okay, there will be no k here, and I get mu by k r square. Okay. And now I have to, if the velocity, if the inertial term and the pressure gradient are comparable, that means that these two terms are comparable. Okay. That means that I have to scale the velocity using this factor. Okay. Using this factor, I have to scale V x star is equal to rho omega V x by k, okay, which means that V x is equal to k V x star by rho omega. Okay. So, this gives me partial V x star by partial t star. Okay. I will give it another index so as not to confuse with the viscous scaling. I will call it as V x plus is equal to minus cos of t star plus mu by k r square, and then I get this additional factor here. Okay, when I express it in terms of the scaled velocity, I get this additional factor here. Okay, that is k by rho omega. Okay. And you can easily verify that this k and k cancel out, and I get mu by rho omega r square. Mu by rho omega r square was the 1 over the Reynolds number, okay, was 1 over the Reynolds number. So, I will get partial Okay. So, this is the equation now. I have high Reynolds number, that means I have a small parameter that is multiplying the viscous term in the equation. Okay. I have a small parameter that is multiplying the viscous term in the equation. How do I solve this? Once again, I write V x dagger. I can write it as some real part of some function of r e power I t. Okay. Substitute this V x dagger is equal to this function of r times e power I t into the equations. Okay. And what I will get is that, okay, the derivative with respect to time just gives me an I. Okay. V x double dagger is equal to minus 1, sorry. There should be an e power I t here. Okay. Okay. Into e power I t star. And this common factor of e power I t cancels everywhere. Okay. and I get I Vx double dagger is equal to, should be a minus sign, my apologies, there should be a minus sign here because there is a minus cos of t. And there should be a factor of 1 over R e. So, and in the limit as R e omega is large, this number is small. Okay. So, to recall, you expressed the velocity Vx, scaled it by inertial scales. Okay. So, Vx dagger is the velocity scaled by inertial scales over here. Substituted that into the equation. Written cos of e power t, cos of t star as the real part of e power I t star, and expressed Vx dagger as the real part of Vx double dagger times e power I t star. Substituted that into the equation. Okay. And divided throughout by e power I t star. Okay, and then I get an ordinary differential equation for this Vx double dagger. So, to get the actual velocity, I have to multiply Vx double dagger by e power I t and then take the real part as indicated here. Now, how do we solve this equation? Okay. You would expect, you would naively assume that in the limit as the Reynolds number is very large, I can neglect this viscous term. Okay. So, if I neglect this viscous term, the equation just reduces to I Vx double dagger is equal to minus 1, okay, which implies that Vx double dagger is equal to minus 1 by I, which is the same as I, because I square is minus 1. Okay. So, I have minus 1 is I square in the numerator. Okay. Substitute this back into the equation. Okay. Vx double dagger is equal to, Vx dagger is equal to the real part of Vx double dagger e power I t, which is equal to the real part of I into cos t plus I sin t. This is just equal to minus sin t. Okay. And now we have to apply the boundary conditions. Okay. We have to apply the boundary conditions, that is at r star is equal to 0, the symmetry condition, partial, or in this particular case the total derivative by dt by dr is equal to 0, and you can see that since Vx double dagger is a constant, it does satisfy that condition. Okay. Second is at the surface, at the wall of the pipe at r star is equal to 1, Vx double dagger is equal to 0. This boundary condition is obviously cannot be satisfied. Okay. This boundary condition obviously cannot be satisfied because I do not have any constants in the solution. The reason I do not have constants in the solution is because I have neglected the highest derivative, because it was multiplied by a small parameter. Okay. I have neglected the highest derivative because it was multiplied by a small parameter, and because of this I am not able to, I do not have any integration constants because the second derivative term has been neglected. Okay. And therefore, I got only an ordinary equation which did not contain any constants in it. That is the mathematical reason why we are not able to satisfy the boundary conditions. What is the physical reason? Okay. What is the physical reason? Okay. Note that in the limit of high Reynolds number, I have basically neglected the viscous diffusion term. I have neglected the diffusion term in the momentum equation. Okay. Now, if you look at the flow in a pipe, for example, Okay. If you look at the flow in a pipe, the velocity at the wall has to come to 0. Okay. The velocity at the wall has to come to 0 because of the no slip condition. Velocity decreases to 0 because there is diffusion of x momentum in the radial direction. That is, there is a decelerating effect due to the wall, which is basically diffusion of x momentum in the negative direction, okay, the diffusion of minus x momentum in the radial direction. When we neglected the viscous term, we neglected that diffusion term, okay, and because of that we were not able to satisfy that boundary condition. Now, what does Re omega large mean? It means that over a length scale comparable to the pipe radius r, over a length scale comparable to the pipe radius r, momentum diffusion is much slower than convection, okay, or acceleration. Okay, momentum diffusion is much slower than acceleration. Even when momentum diffusion is small, right, it may diffuse to a distance that is much smaller than the pipe radius, but there has to be diffusion for the momentum to decrease to 0 at the wall. Okay. So, we have to incorporate the effect of momentum diffusion within a thin region close to the wall in order to be able to satisfy the boundary condition. What is the thickness of that region over which momentum diffuses? The thickness of that region will be determined from the condition that momentum convection and diffusion, or rather the acceleration and diffusion, are comparable within that thin region. Okay. That acceleration and diffusion are comparable within that thin region. So, if I look at a thin region close to the wall, okay, if I look at a thin region close to the wall, okay, if the velocity has to go to 0, right, that means that in the center of the channel the velocity is almost a constant, and it comes down to 0 in a thin region close to the wall of thickness that is much smaller than the radius of the pipe, okay, of thickness that is much smaller than the radius of the pipe. So, I can focus my attention on this region, okay, of thickness delta times r, where delta is a small parameter, okay, of thickness delta times r, where delta is a small parameter, okay, the region within which momentum diffusion is comparable to the other terms in the conservation equation. In the limit, as the Reynolds number becomes large, this delta becomes smaller and smaller in such a way that momentum diffusion is comparable to all the other terms in the equation within that thin region. I can define a coordinate, okay, I can define, okay, so this wall is r star is equal to 1, okay. I can define a coordinate in the perpendicular direction to the wall as r star is equal to 1 minus delta times w, okay. Delta is a small parameter, gives you the thickness of that region. Delta decreases to 0 as Re becomes larger and larger. W is a coordinate that is order 1, okay. W is a coordinate that is order 1. So, substitute this r star is equal to 1 minus delta w into the conservation equation, okay. I Vx double dagger is equal to minus 1 plus 1 by Re omega, r star is 1 by 1 minus delta w, okay. D by dr will be 1 by minus 1 by delta d by dw, okay, acting on 1 minus delta w, that is r, into minus 1 by delta d by dw of Vx double dagger. Okay. And since delta is small, I can neglect delta w with respect to 1, okay, and I will get I Vx double dagger is equal to minus 1 plus 1 by Re omega times delta square, okay, d square Vx double dagger by dw square. Okay. Note that I have a 1 over delta here and I have a 1 over delta here, one derivative and a second derivative. So, I get d square Vx by dw square times 1 over Re omega and delta square. So, what is the region within which the viscous term is comparable to all the other terms in the limit as Re omega goes to infinity? That is when this is of order 1, or alternatively delta goes as 1 over Re omega power half. Okay. So, the thickness of this region goes as 1 over Re omega power half in the limit as Re omega goes to 0. That is the region within which there is momentum diffusion, which is comparable to all the other terms in the equation. Okay. So, without loss of generality, okay, I can set delta is equal to 1 over Re omega power half, okay, and the solution becomes I Vx double dagger is equal to minus 1 plus d square Vx by dw square. This is once again, it is a inhomogeneous equation which consists of a general solution, which is a solution of the homogeneous equation d square Vx double dagger by dw square minus I Vx is equal to minus 1. The general part solves the homogeneous equation with the right side set equal to 0. The particular solution is any one solution that satisfies the equation. Simplest particular solution is a constant. Okay. The general solution is of the form Vx double dagger is equal to a e power root I w plus b e power minus root of I w, and the particular solution is just equal to I. Okay. I am sorry, on the right side it should be plus 1. Okay, on the right side it should be plus 1. Okay. And if I write it in terms of the original variables, I get e power root I into Re omega into minus r star plus b e power minus root of I Re omega into 1 minus r star plus I. Okay. Where I have substituted r star is equal to 1 minus delta w. So, that w is equal to 1 minus r star by delta, which is equal to Re omega power half into 1 minus r star. Okay. So, therefore, w is equal to Re omega power half into 1 minus r star. And now I have to apply the boundary conditions. Okay. The first boundary condition is that the disturbance to the velocity, okay, the disturbance, so the velocity has to be 0 at the bottom surface. Okay, the velocity has to be 0 at the bottom surface. As you go upwards, right, the velocity has to go towards the homogeneous solution, that is I. Okay. If you recall that we had got the solution for Vx dagger as just equal to I. Okay. So, this solution that I get from this analysis near the boundary has to converge to this value I. Okay. I have two terms, one of which is exponentially growing and the other is exponentially decaying. Okay. Clearly, it will not converge to I as you go towards the center of the pipe unless this exponentially growing term is equal to 0. Okay, and I get this equal to b e power minus root of into 1 minus r star plus I. Okay. This comes, so A is equal to 0 from the condition that Vx double dagger has to be equal to I for r star going to 0. Okay. Okay, at the center of the channel it has to be equal to I. The second boundary condition is that Vx double dagger is equal to 0 at r star is equal to 1, okay. And therefore, I get a final solution for the velocity as equal to I 1 minus e power minus root of I r e omega, okay, 1 minus r star, okay. So, this provides a solution for the equation, okay, in the entire channel, okay. This part, this one here is near the center. The second part is the correction close to the wall due to viscous diffusion from the wall, okay, is the correction close to the wall due to viscous diffusion from the wall. This term is included so that you get a converged solution in the limit as r e omega becomes large. So, initially we had just neglected the viscous term and we found that we could not satisfy the boundary condition, and that was because the viscous term had the second derivative in it, okay. So, because of that there were no constants of integration. Physical reason was if we neglect the viscous term there is no viscous diffusion and therefore, the velocity will not come to 0 at the wall itself. Therefore, we have to include the viscous term within a thin region close to the surface where that viscous term is comparable to all the other terms. If the thickness of that region is small, the gradients are very large and the viscous term contains two derivatives of the velocity. Therefore, even though there is a factor of 1 over r e omega which is small, if the derivatives are large, the product of those two could be of order 1 and the viscous term could be comparable to all of the other terms in the equation, okay. And therefore, we got a solution by postulating a thin viscous boundary layer close to the surface where the viscous terms are comparable to the other terms. The thickness of that region was obtained from the condition that in the limit as the Reynolds number becomes large, this term is comparable to all the other terms in the equation, and we found that that boundary layer thickness was 1 over r e omega power half, okay. And we rescaled the equation and then we were able to solve it due to by incorporating the diffusion from the boundary, okay, within this thin region whose thickness decreases as the Reynolds number increases in such a way that the viscous term is comparable to all the other terms, or rather viscous diffusion is comparable to the acceleration and the pressure gradient within this thin boundary layer. And this procedure is what is called a singular perturbation. Where the viscous term is where the problem contains a small parameter. If you set that small parameter multiplies the highest derivative, if you set that small parameter equal to 0, then you find that the highest derivative disappears and therefore, you are not able to satisfy the boundary conditions. You have to postulate that the highest derivative is large over a length scale close to the surface, such that the small parameter times that highest derivative is comparable to all of the other terms in the equation. So, that is the physical reason why in the limit of high Reynolds number there is a boundary layer close to the surface where diffusion is important even in the limit as the Reynolds number becomes very large. So, this completes our discussion of unidirectional transport. I will go on to looking at the diffusion equation in the next lecture. I will see you then.